Look up at the night sky, and what do you see? A scattering of stars, perhaps a planet or two, the faint glow of the Milky Way. It's beautiful, but it feels random, disconnected, almost like glitter thrown across black velvet. But what if I told you that what we see is only the surface, just the barest hint of something far grander, far more intricate, hiding just beyond our sight? What if the universe isn't chaotic or accidental, but structured, woven together by an invisible architecture so vast and complex it defies imagination? This hidden framework, what scientists often call the cosmic skeleton, is one of the greatest mysteries in all of modern science, and it doesn't just shape the stars and galaxies, it dictates the very fate of the cosmos itself. This isn't science fiction, it's the frontier of our understanding, a reality being uncovered piece by piece through revolutionary tools and profound theories. In this video, we're setting out on a journey to map this hidden skeleton of the universe. We'll explore how dark matter, an unseen, mysterious substance, acts as the scaffolding for everything that exists. We'll follow the ghostly threads of cosmic filaments that guide galaxies into place like rivers guiding leaves. We'll see how gravity, the master sculptor of the cosmos, has been carving this grand design since the first moments after the Big Bang. And we'll discover why understanding this architecture isn't just important for scientists, it redefines our place in the universe, connecting us to a story billions of years in the making. So prepare to see the cosmos in a whole new light. We're going to peel back the layers of reality, from the largest superclusters to the emptiest voids, and expose the hidden bones of existence. By the end of this journey, you won't just look up at the night sky, you'll feel it, sense the structure humming silently in the darkness, and understand that we are part of something far greater than we ever knew. Forget everything you thought you knew about the universe being a random collection of stars. The truth is far more structured, more intricate, and frankly, more beautiful. Picture, if you will, the universe on its very largest scale, not as a simple scattering of glitter, but as something far more complex, a vast three-dimensional tapestry. This is the cosmic web, the fundamental architecture of all that exists. Imagine the neural network of a brain with its interconnected nodes and pathways, or a colossal spiderweb glistening with morning dew, but stretched across billions of light years. This web isn't made of silk, of course, but of the gravitational pull of dark matter, tracing out filaments that stretch across the unimaginable emptiness of space. These filaments connect at dense junctures, massive nodes where thousands of galaxies swarm together in clusters, and between them lie the great cosmic voids, regions of breathtaking emptiness that make up most of the universe's volume. This grand design didn't form by accident. It is the direct result of gravity acting over billions of years on the faintest ripples left over from the Big Bang. But how do we map something so vast and largely invisible? We use the most powerful tools at our disposal. Supercomputers run complex simulations, calculating the gravitational dance of trillions of particles of dark matter to predict where this web should be. Then we point our most advanced telescopes, like Hubble and the James Webb Space Telescope, out into the depths to see if the prediction matches reality. And it does, by charting the precise positions and movements of millions of galaxies. We see them lining up along these predicted invisible threads, flowing like water through riverbeds in space. They congregate at the intersections, confirming the nodes, and they avoid the voids, outlining their immense borders. This framework is the absolute bedrock of modern cosmology. It explains how our universe evolved from a hot, dense, and nearly smooth primordial soup into the complex hierarchy of structures we observe today: stars, galaxies, clusters, and superclusters, all embedded within this larger skeleton. Understanding this web is the first and most crucial step in our journey to map the hidden skeleton of the cosmos, setting the stage for us to meet its primary architect, the mysterious substance known as dark matter. But if the cosmic web is the grand architecture of the universe, then dark matter is the invisible, uncanny material from which its entire framework is built. Think of the most magnificent cathedral you can imagine. You marvel at its stained glass, its soaring arches, its intricate stonework, all the things you can see. Yet the entire structure is only possible because of the hidden, load-bearing steel and concrete you never lay eyes on. That is the role dark matter plays for the cosmos. It is the unseen scaffolding, the essential support system that holds everything together, yet it reveals itself not through light, but solely through its immense gravitational influence. We now know this mysterious substance makes up roughly 27% of all the mass and energy in the universe. That is over 5 times more than all the atoms, stars, planets, and gas that we can actually see. Its gravitational pull is the primary force that sculpted the cosmic web, acting like a template upon which ordinary matter could slowly accumulate. It's the reason galaxies cluster along those vast filaments and why they form immense, spherical halos that extend far beyond their visible stars. Without the relentless gravitational grip of this dark matter halo surrounding them, the incredible rotational speeds of stars within a galaxy would simply fling them out into the void. The galaxy would tear itself apart. The very fact that we have stable, long-lived galaxies is one of the most compelling pieces of evidence that this invisible scaffolding must exist. So how do we study something that is, by its very nature, undetectable to our telescopes? We observe its profound effects on the things we can see. One of the most powerful techniques is gravitational lensing. This is a dramatic confirmation of Einstein's theory of general relativity, where the gravity of a massive object like a cluster of galaxies warps the very fabric of space-time around it, bending and distorting the light from galaxies that lie far behind it. By meticulously mapping these distortions, astronomers can literally chart the distribution of the mass causing the warping, and time and again, they find that the vast majority of that mass is invisible. It's the dark matter, revealing its presence by the way it bends the path of light itself. On another front, scientists are trying to create it or detect it directly here on Earth. Deep underground in ultra-sensitive labs, detectors wait for the incredibly rare moment a dark matter particle might bump into an ordinary atom. Meanwhile, immense machines like the Large Hadron Collider smash particles together at nearly the speed of light, hoping to recreate the conditions of the early universe and potentially manufacture dark matter particles for a fleeting instant. Despite these heroic efforts, its fundamental nature remains one of the greatest unsolved puzzles in all of physics. Is it a particle, a family of particles? Something even more exotic that we haven't yet conceived of. We simply do not know. Yet understanding this enigmatic substance is absolutely key to mapping the hidden skeleton of the cosmos, because it is the dark matter that dictates where the visible universe, our universe of light and life, gets to call home. So if dark matter is the invisible scaffolding, then where does the beautiful, luminous universe we actually see come into the picture? The answer lies along the cosmic rivers, the vast filaments of the web where the raw materials for galaxy construction are channeled and concentrated. Picture a great river system on Earth, with smaller streams feeding into larger tributaries, all flowing toward a central confluence. Now imagine that on a cosmic scale, where the rivers are flowing with dark matter and primordial gas, and the confluences are the dense nodes of the web. This is where galaxies are born. It's not a random, chaotic process. It's a highly organized delivery system, a galactic conveyor belt that has been running for billions of years. The journey begins when clouds of hydrogen gas, the leftover fuel from the Big Bang, are pulled by gravity into these filamentary channels. They stream along these invisible roadways, cooling and condensing as they travel. But the real magic happens at the intersections, where these cosmic rivers of dark matter meet and tangle. Their gravitational pull is at its absolute strongest. It's at these busy interchanges that the gas piles up, becoming dense enough to finally collapse under its own weight and ignite the fires of the first stars. These are the seeds of galaxies. Over time, these infant stellar systems continue to draw in more gas and even smaller galaxies from the filament itself, growing and evolving as they are fed by this constant flow. It's a form of cosmic nourishment, with the filaments acting as the umbilical cords for galactic growth. This isn't just a beautiful theory. We have overwhelming observational evidence. Massive sky surveys, like the monumental Sloan Digital Sky Survey, have meticulously mapped the positions of millions of galaxies. When we look at these maps, a stunning pattern emerges. Galaxies are not scattered randomly. They are meticulously aligned, strung out along these vast, invisible lines like pearls on a string. Even more fascinating, the galaxies that lie along these filaments are different. They tend to be younger, more actively forming stars, and they often have a specific orientation, with their disks aligned with the filament itself, as if they were all rolling down the same cosmic track. This alignment is a direct signature, a fossil record of their formation within the flow. It's the visible proof of how the hidden architecture of dark matter directly dictates the properties of the luminous universe we observe. And this dance continues over cosmic time. Galaxies are not static islands. They are in constant motion, migrating along these filaments over billions of years. They flow from the less dense regions toward the massive clusters that sit at the web's nodes, drawn in by the immense gravitational pull of these crowded metropolitan centers. This journey shapes their destiny. A small galaxy drifting into a dense cluster can have its gas, its star-forming fuel stripped away by the hot intracluster medium, transforming it from a vibrant spiral into a quiet, red and dead elliptical galaxy. By tracing the paths of these galaxies and understanding their properties, astronomers can effectively reverse engineer the history of the cosmic web, using the galaxies themselves as tracers to map the invisible skeleton that guides them. This grand, choreographed migration, all driven by the relentless pull of gravity, sets the stage for understanding the fundamental force that designed this entire system in the first place. But if dark matter provides the raw framework and cosmic filaments act as the delivery routes, then gravity is the master artist, the invisible hand that tirelessly sculpts this entire cosmic architecture. It is the fundamental force that takes the formless potential of the early universe and patiently, over billions of years, carves it into the breathtaking complexity we observe. Without gravity, the cosmos would remain a featureless, expanding cloud of particles, a dilute and homogeneous soup with no stars, no planets, and certainly no one to wonder about its existence. It is the great organizer of the universe, the force that draws matter together and constructs everything from the smallest asteroid to the largest supercluster. This sculpting process began with the most minuscule of beginnings. In the first fraction of a second after the Big Bang, the universe was incredibly hot and dense, but not perfectly smooth. Thanks to the quantum frenzy of that era, there were tiny, random fluctuations in density regions that were ever so slightly denser or less dense than their surroundings. These imperfections were the seeds of all future structure, and gravity was the force that nurtured them. A region with just a little bit more matter had a slightly stronger gravitational pull, which attracted even more matter from its surroundings. This, in turn, made its gravity even stronger, creating a powerful feedback loop of growth. Over cosmic time, these tiny overdensities were amplified into the vast cosmic web, with the slightly denser regions becoming the nodes and filaments, and the underdense regions evolving into the great voids. It was a slow, relentless process of accumulation, a gravitational instability that turned the faintest whisper of unevenness into a roaring chorus of structure. Our modern understanding of how this works is rooted in Einstein's revolutionary theory of general relativity. This framework revealed that gravity is not merely a force pulling objects together in a fixed space, as Newton described. Instead, it is the curvature of the very fabric of space and time itself. Imagine space-time as a vast, taut rubber sheet. Place a massive object like a star or a galaxy on that sheet, and it creates a deep dimple or well. Now, any other object moving nearby will have its path altered as it rolls along the curves of this warped sheet. This is the essence of gravity. Mass tells space-time how to curve, and curved space-time tells mass how to move. On the grandest scales, the collective gravity of all the dark matter in the universe warps the cosmic rubber sheet into an immense, complex landscape of hills and valleys. The filaments of the cosmic web are like the ridges between these valleys, and the great clusters are the deepest gravitational wells where matter has pooled from across billions of light years. We can witness the evidence of this curvature through incredible phenomena like gravitational lensing, where the gravity of a massive galaxy cluster acts as a cosmic magnifying glass, bending the light from even more distant galaxies behind it into beautiful, stretched arcs and rings. This not only provides a direct snapshot of gravity's influence on light itself, but also allows astronomers to map the distribution of both dark and visible matter, creating a more complete picture of the cosmic skeleton. Furthermore, through sophisticated computer simulations that run the equations of general relativity backwards and forwards across 13.8 billion years, scientists can watch this entire process unfold. They start with the observed faint ripples from the cosmic microwave background and let gravity do its work, virtually growing the cosmic web in a digital universe. The stunning agreement between these simulations and the actual large-scale structure we observe with our telescopes is one of the most powerful validations of our understanding, confirming that gravity alone, acting on dark matter, is the primary architect of the universe's invisible architecture. This pervasive influence from the quantum scale to the cosmic establishes gravity as the fundamental sculptor of reality, a force that took the raw materials of the early universe and patiently crafted them into the complex and beautiful cosmic blueprint we are only now beginning to map. To truly grasp the origin of the cosmic skeleton, we must journey back to the very beginning, to a time before stars, before galaxies, before even atoms had formed. We have to rewind the tape of the universe all the way to its first fleeting moments. In that initial fiery state, the cosmos was a searingly hot, incredibly dense, and almost perfectly smooth sea of energy and fundamental particles. Almost is the most important word in that sentence, because if it had been perfectly smooth, our universe would have remained that way, a featureless, expanding fog. For structure to form, for gravity to have something to work with, there had to be seeds. There had to be tiny, microscopic imperfections, places that were just a little bit denser than others. The question is, where did these crucial irregularities come from? The answer lies in a bizarre and poorly understood period called inflation, a fraction of a second after the Big Bang, where the universe is thought to have expanded faster than the speed of light, ballooning from smaller than a proton to something perhaps the size of a grapefruit in an almost unimaginably short time. This violent stretching didn't just make the universe big, it also magnified the most fundamental kind of chaos. According to quantum mechanics, empty space is not truly empty. At the tiniest scales, it is a foaming, bubbling sea of virtual particles constantly flickering in and out of existence. These are quantum fluctuations, brief violations of energy conservation that are a normal part of the subatomic world. During the frantic expansion of inflation, these tiny, random quantum fluctuations were suddenly stretched from the subatomic to the cosmic scale. Imagine drawing a tiny, wiggly line on a deflated balloon. Now blow that balloon up to the size of a house. That tiny, random wiggle becomes a large, macroscopic feature. Inflation did exactly that to the fabric of space-time itself. It took these infinitesimal quantum ripples and imprinted them as minute differences in the density of matter and energy across the entire newborn universe. These weren't large variations, just tiny, 1 part in 100,000 fluctuations, but they were enough. They were the primordial seeds. They were the universe's original blueprint, the genetic code from which every galaxy, star, and planet would eventually grow. For hundreds of thousands of years, the universe remained too hot and energetic for these seeds to do anything. It was a thick, opaque plasma of particles and light. But then, about 380,000 years after the Big Bang, a pivotal event occurred. The universe cooled enough for atoms to form, allowing light to finally travel freely. That first flash of light, now stretched and cooled by the expansion of the universe, still fills all of space. We detect it today as the cosmic microwave background, or CMB, a faint, cold whisper of radiation that is the oldest light we can see. And it is in this ancient afterglow of creation that we can directly observe those primordial seeds. Missions like the Planck satellite have spent years meticulously mapping the tiny temperature variations in this background radiation. The result is a spectacular, full sky map that looks like a celestial fingerprint. The slightly warmer, reddish spots correspond to those regions of the infant universe that were ever so slightly denser, the ones that inherited a little extra mass from those inflated quantum fluctuations. The cooler, bluish spots are the underdense regions. This map is not random static. It is a detailed baby picture of the cosmos, showing the precise arrangement of the density seeds that would dictate all future structure. The patterns we see in this light from 13.8 billion years ago are a perfect statistical match for the distribution of galaxies we see in our sky today. The blueprint encoded in that light predicted the cosmic web with astonishing accuracy long before our telescopes were powerful enough to see it. This profound connection is one of the greatest triumphs of modern cosmology. It means that the largest structures we can observe, the vast superclusters and filaments spanning hundreds of millions of light years, have their origin in the tiniest, most quantum of events. The hidden skeleton of the cosmos wasn't built later. Its potential was woven into the fabric of the universe from the very first instant. Everything was set in motion from the beginning, a cosmic destiny written in the cold, faint light of the Big Bang's aftermath, waiting patiently for billions of years for gravity to slowly, meticulously, sculpt those tiny seeds into the grand and glorious architecture we are now beginning to map. But how do we move from theory to a tangible map? How do we chart the invisible? The answer lies in a powerful synergy between the digital and the observational, a partnership between supercomputers that simulate the universe and telescopes that peer into its deepest realms. This is the art and science of cosmic cartography, and it relies on two complementary toolkits: virtual universes created in silicon and real-world observations captured by the most advanced instruments ever built. On one front, cosmologists wield immense supercomputers to run what are called n-body simulations. These are not simple animations. They are incredibly complex mathematical models that use the known laws of physics, primarily gravity, to track the movement of billions, even trillions, of individual particles of dark matter over the entire age of the universe. Scientists start with the initial conditions we see in the cosmic microwave background, those tiny density fluctuations, and then let the simulation play out. They watch as gravity works its magic, seeing if those faint ripples naturally evolve into a familiar cosmic web of filaments, nodes, and voids. The most sophisticated simulations, with names like Illustris TNG and Millennium, don't just track dark matter. They also incorporate the messy physics of normal matter, the gas that cools, forms stars, and is blown out again by supernova and black holes. Running these simulations is a monumental task, requiring millions of hours of computing time and generating petabytes of data. But the result is a breathtakingly detailed, dynamic atlas of a virtual universe, a prediction of what the cosmic skeleton should look like based on our best theories. Of course, a prediction is only as good as the evidence that supports it. This is where our telescopes come in, serving as the reality check for these digital universes. Ground-based observatories like the Vera Rubin Observatory in Chile conduct massive redshift surveys. By capturing the light from millions of galaxies, they can measure a phenomenon called redshift. As the universe expands, it stretches the wavelength of light from distant galaxies, making it appear redder. The degree of this redshift tells us how far away a galaxy is, and by measuring the redshifts of countless galaxies, we can create a three-dimensional map of their positions in space. These maps from projects like the Sloan Digital Sky Survey reveal the large-scale structure in stunning detail, showing galaxies clustered into filaments and walls, exactly as the simulations predicted. To peer even deeper, we turn to space telescopes like the Hubble and the James Webb Space Telescope. JWST, in particular, is a game-changer. Its incredible infrared sensitivity allows it to look back to the very earliest galaxies, witnessing the first stages of cosmic web assembly. It can see the faint glow of hydrogen gas within the filaments themselves, the raw material flowing into the growing nodes. This allows us to not just map the galaxies that trace the web, but to potentially begin mapping the gaseous bones of the skeleton directly. And for the most hidden mass, we use gravity itself as a tool through gravitational lensing. By studying how the light from distant, background galaxies is warped and distorted as it passes through the gravitational field of a foreground galaxy cluster, astronomers can create a precise map of the cluster's total mass, including the vast halo of dark matter that surrounds it. This technique effectively turns a galaxy cluster into a natural magnifying glass, revealing the distribution of the invisible scaffolding. It's like deducing the shape of a glass lens by carefully watching how it bends beams of light. By combining all these methods, simulations, redshift surveys, deep imaging, and lensing, scientists perform a kind of cosmic triangulation. They cross-reference the predictions from their digital universes with the hard data from their telescopes, refining their models and inching closer to a complete and accurate map of the hidden architecture that defines our existence. Yet for all our sophisticated tools and brilliant theories, mapping the true structure of the cosmos remains one of the most daunting challenges in all of science. The sheer scale alone is almost incomprehensible. We are trying to chart a web of dark matter filaments that can stretch for hundreds of millions of light years, structures so vast they dwarf the very galaxies that trace them out. And these cosmic threads are not only enormous, they are also incredibly subtle. While we can see the galaxies that cluster along them like lights on a highway, the filaments themselves are composed of diffuse, dark matter and incredibly thin, hot gas that emits almost no light for our telescopes to catch. We are, in essence, trying to map the invisible by the sparse arrangement of the visible, like trying to deduce the shape of a breeze by watching how a handful of leaves are carried along by it. Our entire understanding of this hidden skeleton relies on indirect evidence, on measuring the gravitational effects of something we cannot see. This challenge is compounded by a fundamental limitation of astronomy. We are always looking into the past. The finite speed of light means that when we peer at a galaxy a billion light-years away, we are seeing it as it was a billion years ago. This creates a complex, layered view of the universe. As we map the positions of galaxies at different distances, we are not creating a single snapshot of the cosmic web as it exists today, but rather a patchwork quilt of its structure at different epochs in its history. We see the younger, still-forming skeleton in the distant universe and the more evolved, mature architecture closer to home. Piecing this together into a coherent, current map is like trying to understand the complete growth of a forest by examining a single tree's rings, a sapling a mile away, and a mature tree on the horizon, all at the same time. It requires intricate models to connect these different slices of cosmic time into a single, evolving picture. Adding another layer of complexity are the lingering uncertainties in our fundamental cosmological parameters. Our maps and simulations depend on precise values for things like the density of dark matter and the strength of dark energy. But what if our understanding of dark energy's nature is incomplete? If its properties have changed over time, it would dramatically alter how we model the growth of the cosmic web throughout history. Similarly, the exact properties of dark matter particles, whether they are cold, warm, or something else, influence how easily small structures form, which in turn affects the fine details of the web's architecture. It's a two-way street. We use the observed cosmic web to constrain these parameters, but our uncertainty about the parameters themselves means there is still a range of possible models that could explain what we see. We are simultaneously trying to read the map and figure out the legend needed to understand it. Despite these formidable obstacles, the progress we have made is nothing short of revolutionary. The hurdles themselves have become catalysts for innovation. The need to see the unseen has driven the development of exquisite gravitational lensing techniques, turning warped starlight into a precise scale for weighing dark matter. The challenge of processing the unimaginable flood of data from sky surveys has propelled advances in machine learning and artificial intelligence, which now help us identify patterns and structures within the data that the human eye might miss. Each limitation forces a new level of creativity, and with every passing year, our digital simulations grow more detailed, our telescopes more sensitive, and our statistical methods more powerful. This relentless perseverance in the face of such profound mystery is a testament to human curiosity, and it is steadily turning the invisible architecture of the cosmos from a theoretical concept into a mapped reality. While our maps of the cosmic web are built on theory and simulation, it is the astounding, real-world discoveries that truly bring this invisible architecture into sharp, undeniable focus. These are the moments where the hidden skeleton suddenly and spectacularly reveals itself. One of the most profound of these revelations came not from finding something massive, but from discovering a breathtaking nothingness. In the 1980s, astronomers mapping the distribution of galaxies stumbled upon a region in the constellation of Boötes so vast and so empty it defied comprehension. The Boötes void, often nicknamed the Great Nothing, is a spherical region of space roughly 330 million light-years across. To put that in perspective, if our Milky Way were at the center, we wouldn't have encountered another galaxy for tens of millions of light-years in every direction. This wasn't just a gap, it was a cosmic desert on a scale that existing models had a hard time explaining. Its discovery was a landmark moment because it forced science to stop thinking of voids as mere background and to start seeing them as fundamental, active components of the cosmic web. These vast empty spaces are not accidental. They are the inevitable counterpart to the dense filaments, sculpted by gravity and playing a crucial role in the overall dynamics and evolution of the entire universe. The Boötes void taught us that to understand the skeleton, we must study the empty spaces between the bones just as intently as the bones themselves. If the Boötes void showed us the importance of emptiness, another monumental discovery helped us find our own address within the grand metropolitan structure of the cosmos. For centuries, we knew our Milky Way was part of a local group of galaxies, which was part of the Virgo cluster, but the larger structure remained murky. That changed in 2014 with the definition of the Laniakea supercluster, using a revolutionary technique to map the peculiar velocities of thousands of galaxies, that is, how they deviate from the overall expansion of the universe due to local gravitational tugs. A team of astronomers was able to trace the flow of galaxies across space. They discovered that our entire local region, including the Virgo cluster and many other groups, is part of a single, immense river of galaxies, all flowing together under the gravitational influence of a phenomenally massive attractor. This structure, named Laniakea, meaning immeasurable heaven in Hawaiian, is a gravitational watershed, a continent of galaxies spanning over 500 million light-years. Seeing this map for the first time was like looking at a globe and finally seeing the continent you live on. It redefined our home, showing that we are not just in a cluster, but on a specific filamentary arm of a supercluster, flowing toward a hidden gravitational center. This was a direct, observational map of the cosmic web's gravitational currents, a stunning confirmation that the universe's large-scale flows are dictated by the invisible architecture of dark matter. Perhaps the most compelling validations of our cosmic models come from looking not at the present structure, but at its ancient, fossilized imprint. The detailed mapping of the cosmic microwave background radiation by satellites like WMAP and Planck provided nothing less than the original blueprint for the entire cosmic skeleton. These missions spent years measuring the faint temperature variations in that ancient light, the afterglow of the Big Bang, with exquisite precision. The resulting full sky maps are a cosmic Rosetta Stone. The pattern of hot and cold spots they revealed is a precise snapshot of the density fluctuations in the infant universe, the very seeds from which all structure would grow. The power of this discovery lies in its predictive power. The statistical properties of these tiny fluctuations, measured when the universe was only 380,000 years old, perfectly predict the statistical distribution of galaxies and clusters we observe billions of years later. It is a direct line of evidence connecting the quantum ripples of the beginning to the grand design we see today. The Planck satellite's results, in particular, confirmed the standard cosmological model with remarkable accuracy, providing the precise initial conditions that our supercomputer simulations need to successfully grow the cosmic web. This agreement between the universe's baby picture and its current adult form is one of the most powerful triumphs of modern science, proving that our understanding of the hidden skeleton's origin is fundamentally correct. Each of these milestones, from the great nothingness of Boötes to the continental flow of Laniakea to the primordial blueprint of Planck, serves a dual purpose. They act as vital validations, giving us immense confidence that we are on the right track in our quest to map the cosmos. But perhaps just as importantly, they ignite new questions and open new frontiers. The Boötes void makes us wonder what rare, isolated galaxies might exist within it and how they formed. Laniakea forces us to ask what lies at the heart of the great attractor pulling us forward. And the incredible precision of the Planck data also revealed subtle anomalies like the mysterious cold spot that hint there might still be physics beyond our current models. Every answered question gives rise to a deeper, more nuanced one, ensuring that the process of discovery is never truly complete. These key findings are the cornerstones upon which our understanding is built, the brilliant flashes of light that illuminate the hidden framework, bringing us closer than ever to a complete map of the cosmic skeleton. But the cosmic web is defined not only by the dense, glittering filaments where galaxies swarm, but equally by the immense, silent spaces in between. If the filaments are the continents of the cosmos, then these regions are the great, empty oceans, vast, underdense expanses known as cosmic voids. To truly appreciate the full architecture, we must turn our attention to these pockets of nothingness, which collectively make up the overwhelming majority of the universe's volume. A single void can stretch for hundreds of millions of light-years, a sphere of space so cavernous that if you were to place our Milky Way at its center, the nearest major galaxy would be tens of millions of light-years away, a lone, distant island in a sea of near emptiness. It's a common misconception to think of these voids as completely barren. They are not perfect vacuums. Instead, they are the cosmic equivalent of a deep desert, sparsely populated, but not entirely devoid of life. They contain a thin sprinkling of isolated, often peculiar galaxies that have managed to form in this impoverished environment, along with wispy clouds of hydrogen gas and, of course, the ever-present dark matter. But the density of matter here is far, far lower than in the bustling filaments and clusters. This profound difference in density is not passive. It is dynamically active, shaping the evolution of the entire cosmic web. According to Einstein's theory of general relativity, it is not just mass that creates gravity, but also differences in pressure. The incredibly low density inside a void creates a kind of effective repulsive force. Think of it like being in a crowded room where everyone is pushing toward the snack table. You find it easier to move away from the dense crowd into the empty space. In a similar way, the higher density regions surrounding a void have a stronger gravitational pull than the void itself, causing matter to effectively flow away from the underdense center and toward the denser filaments. This outflow helps to sharpen the boundaries of the filaments and further empty out the void, in a self-reinforcing cycle that defines the architecture. This dynamic has a direct impact on the galaxies that find themselves inside these emptinesses. A galaxy born or stranded in a void is like a town isolated in the wilderness, cut off from the trade routes and resources of the major cities. Without a constant influx of new gas from the filamentary highways, star formation in these void galaxies often sputters out more quickly, leaving them older, redder, and more quiescent than their cousins in the dense clusters. Their isolated existence makes them fascinating laboratories for studying galaxy evolution in its most stripped-down form, free from the complex interactions that dominate cluster life. Furthermore, the expansion of the universe doesn't happen at a single uniform rate. Space within these enormous voids actually expands slightly faster than the cosmic average, tugging gently at the galaxies within them and providing a unique environment to test our models of dark energy and cosmic acceleration. By studying the profound emptiness of these spaces, we are not just looking at the absence of something. We are studying a fundamental and active component of the cosmic skeleton, whose repulsive gravity and accelerated expansion are essential forces in the eternal dance between construction and emptiness. This grand cosmic architecture is far from a static sculpture frozen in time. It is a living, breathing, and ceaselessly dynamic system, a vast network in constant motion where rivers of galaxies and streams of intergalactic gas flow along the invisible filaments of dark matter. This motion is not random wandering. It is a directed gravitational migration, a cosmic traffic flow dictated by the relentless pull of the web's most massive structures. Galaxies are swept along these channels, drawn by the immense gravitational tides generated by their neighbors and the dense clusters that act like powerful magnets at the intersections. This movement is the lifeblood of the web, a continuous cycle of delivery and redistribution that shapes everything within it. The consequences of these flows are profound and transformative. As galaxies are funneled along these cosmic highways, they don't travel alone. They are surrounded by vast reservoirs of primordial hydrogen gas, the raw fuel for star formation. When this flowing gas is suddenly compressed, whether by entering a dense cluster environment, colliding with another stream of gas, or simply piling up at a filament's confluence, it can trigger an explosive burst of starbirth. We see this in brilliant starburst galaxies, their luminosity dramatically enhanced by the fresh influx of material. Conversely, these same dynamic forces can have a destructive, yet equally creative influence. The gravitational tides within clusters can strip smaller galaxies of their gas, quenching their ability to form new stars and leaving them as passive, aging relics. Meanwhile, at the hearts of galaxies, supermassive black holes are fed by these same gas flows. As matter spirals inward, it is heated to incredible temperatures, lighting up as brilliant quasars or active galactic nuclei that can outshine their entire host galaxy, pouring energy back out into the web and regulating further growth. The end points of these long migrations are the great metropolitan hubs of the cosmos, the massive galaxy clusters that sit at the nodes of the web. These are not merely collections of galaxies, they are the final destinations for matter flowing along the filaments. Numerical simulations show this process in stunning detail, revealing how over billions of years, the gravitational pull of a nascent cluster draws in galaxies and gas from multiple filamentary directions. The cluster grows like a city at the junction of several major rivers, accumulating immense mass and becoming the most gravitationally bound structures in the entire universe. Yet, even as matter pools at these nodes, other parts of the web are stretching. The cosmic voids, those vast empty regions, are not passive bystanders. Their expansion is accelerated by the repulsive effect of their own low density and the overarching influence of dark energy, causing the filaments themselves to stretch and grow thinner over cosmic time. This creates a universe of constant tension between the gravitational collapse that builds clusters and the expansion that stretches the voids, between the inflow of matter and the outflow of energy. By meticulously studying these dynamics, the speeds of galaxies, the shock heating of gas in filaments, the growth of clusters, astronomers do more than just understand the universe's current state. They gain a powerful window into its history and its ultimate fate. The patterns of motion we observe today are a direct echo of the initial conditions set by the Big Bang, evolved over 13.8 billion years under the unyielding influence of gravity. They allow us to rewind the cosmic tape and test our models of the universe's evolution. This intricate gravitational interplay, from the smallest tidal interaction to the largest flow, is what has sculpted the visible universe from a formless primordial soup into the structured beauty we see today. It emphasizes that to truly comprehend the cosmic skeleton, we must understand it not as a static blueprint, but as a narrative, a story of constant, dynamic change where the invisible dance of dark matter sets the rhythm for everything we see. While dark matter provides the gravitational blueprint for the cosmos, it is the ordinary, everyday matter, the stuff of stars, planets, and life itself, that paints the visible picture we can actually observe. This is baryonic matter, the familiar atoms of hydrogen, helium, and all the heavier elements forged in stellar furnaces. If the cosmic web is a sculpture, dark matter is the invisible armature, but baryonic matter is the clay that gives it a visible form, allowing us to trace the outlines of the hidden skeleton. This tangible component fills in the details, making the grand but invisible architecture partially observable to our telescopes and instruments. It acts as a luminous tracer, a cosmic die that reveals the flow and structure of the universe's underlying framework. We can detect this ordinary matter in several key ways, especially within the vast filaments of the cosmic web. The immense clouds of hot gas that flow along these dark matter highways are often too diffuse to emit visible light, but they are searingly hot, reaching temperatures of millions of degrees. At these extremes, the gas glows brightly in high-energy X-rays. Space observatories like NASA's Chandra X-ray Observatory are specifically designed to see this faint, high-energy emission, allowing astronomers to literally map the warm hot gas that weaves through the cosmic filaments, revealing their locations and structures. Another method involves looking for the absorption of light. When the light from a distant, brilliant quasar travels across billions of light years to reach us, it passes through these intervening filaments. Specific elements within the filaments, like hydrogen, will absorb very particular wavelengths of that light, creating a unique fingerprint in the quasar's spectrum. By analyzing these absorption lines, scientists can determine the composition, temperature, and density of the gas in the filament, effectively using distant quasars as cosmic flashlights to illuminate the otherwise invisible bones of the universe. Massive sky surveys provide even more direct evidence of how baryons trace the dark matter backbone. Projects that map the distribution of neutral hydrogen gas across the sky, using its characteristic 21-centimeter wavelength emission, show that this fundamental building block of stars follows the same large-scale patterns as the dark matter. Similarly, surveys that pinpoint regions of intense star formation, like the glowing clouds of nebulae, consistently find them aligned along the predicted filaments and clustered at the nodes. This confirms that the visible universe is indeed sculpted by the invisible hand of dark matter. The galaxies and the gas that forms them are simply following the gravitational contours of the hidden skeleton. However, the relationship is not a simple one-way street where dark matter dictates and baryons obediently follow. The ordinary matter has its own complex physics that can push back, adding fascinating layers of complexity to the structure. This is due to powerful feedback processes. When massive stars reach the end of their short lives, they explode as supernovae, ejecting their outer layers at tremendous speeds and flooding their surroundings with energy. Similarly, supermassive black holes at the centers of galaxies can become active, swallowing material and blasting out colossal jets of radiation and particles. These events inject enormous amounts of energy into the surrounding gas, heating it up and even driving powerful galactic winds that can blow star-forming fuel clear out of a galaxy. This feedback can temporarily shut down star formation, redistribute gas within a galactic halo, and even prevent gas from cooling and falling into a galaxy from the surrounding filament. It means that while the dark matter distribution sets the stage, the baryonic actors have their own scripts, capable of altering the set in dramatic ways. This dynamic interplay is crucial for understanding the fine details of why the cosmic web looks the way it does, explaining, for instance, why some galaxies along a filament are vibrant with new stars while others are quiet and dormant. Ultimately, it is this baryonic matter that provides the tangible, testable evidence for our cosmic models. We cannot yet directly detect dark matter, but we can see its influence etched into the distribution of galaxies and the glow of hot gas. By comparing the precise maps of visible matter created by our telescopes with the predictions of supercomputer simulations that model both dark and ordinary matter, including these complex feedback loops, we can rigorously test our understanding of the entire cosmic system. The agreement between prediction and observation is what gives us such strong confidence in the existence of the dark matter skeleton. As we continue to trace these visible traces with ever greater precision, we begin to uncover the subtle influence of other, even more elusive forces at work within this architecture. While dark matter and gravity lay out the grand design of the cosmic web, and baryonic matter paints its visible features, there is another, even more subtle force silently at work within this architecture, one that is woven into the very fabric of space itself. This is the influence of cosmic magnetic fields. It is a hidden layer of complexity, an invisible web within the web, stretching for millions of light years along the filaments, permeating the voids, and subtly guiding the behavior of everything it touches. These fields are not the simple dipolar magnets of a classroom experiment. They are vast, dynamic, and incredibly powerful, acting as a cosmic weather system that can shepherd gas, accelerate particles to near light speed, and leave an indelible mark on the formation of stars and galaxies. The origins of these immense magnetic fields are a subject of intense study, with two primary theories vying for explanation. One points to primordial beginnings, suggesting that these fields were generated in the incredibly energetic moments after the Big Bang, perhaps during the period of inflation itself. In this scenario, the fields would be a fundamental part of the universe's initial conditions, woven into the cosmic fabric from the very start, and then stretched to cosmic scales by the expansion of the universe. The other major theory points to a more dynamic, ongoing creation process. When galaxies merge, the turbulent chaos of the collision can act like a colossal dynamo, twisting and amplifying any weak, pre-existing magnetic seed fields. Similarly, the powerful shock waves that race through filaments as gas flows into clusters can also generate and strengthen these fields. It is likely that both mechanisms, primordial seeds and astrophysical dynamos, work in concert to create the magnetic landscape we infer today. But how do you measure something that is utterly invisible, that exerts no force on light itself? Astronomers have become detectives, searching for the subtle clues these fields leave behind. One of the most telling pieces of evidence is synchrotron radiation. When high-energy electrons, often accelerated by supernova shocks or active black holes, spiral along the lines of a magnetic field, they emit a very specific kind of radio wave. This emission has a distinctive polarized signature, and by mapping this faint radio glow across the sky, we can literally trace out the magnetic field lines, revealing their structure and strength within galaxy clusters and even along the vast intergalactic highways. Another ingenious method uses the light from distant quasars. As this light travels through magnetized regions of space, the orientation of its waves can be subtly rotated, a phenomenon known as Faraday rotation. By measuring this rotation in the polarized light of background sources, scientists can work backwards to infer the strength and direction of the magnetic fields it passed through on its long journey to Earth. These techniques are painstaking and require incredibly sensitive instruments, but they are gradually pulling back the curtain on this hidden magnetic universe. The influence of these fields, once established, is profound. Within the dense filaments of the cosmic web, they can amplify the shock waves that heat gas, preventing it from cooling too quickly and collapsing to form stars. In this way, they can act as a regulatory valve for star formation on a colossal scale. Conversely, within the quiet depths of cosmic voids, magnetic pressure can provide just enough support to prevent the sparse gas from ever collapsing under its own gravity, helping to maintain the void's emptiness. They also play a crucial role in guiding the most energetic particles in the universe, cosmic rays. These fields act as immense particle accelerators and containment grids, whipping protons and electrons to fantastic energies and directing their flow along the cosmic filaments, effectively creating a network of energy channels throughout the web. This pervasive magnetic influence reminds us that the cosmic skeleton is not shaped by gravity alone. It is a complex structure where multiple forces, gravitational, hydrodynamic, and magnetic, are in a constant dynamic dance. To create a truly complete map of the hidden architecture, we must account for all of these players. The presence of these magnetic fields adds a layer of exquisite complexity to our models, helping to explain finer details that gravity alone cannot, and confirming that the universe is an even richer and more interconnected system than we often imagine. Now, just as we begin to appreciate the intricate interplay of gravity, dark matter, and even cosmic magnetism in shaping the universe, we encounter a plot twist of cosmic proportions, a force that operates in direct opposition to the very gravity that built the cosmic web. For most of the 20th century, astronomers believed the universe's expansion, sparked by the Big Bang, was gradually slowing down. It seemed logical. The gravitational attraction of all the matter in the cosmos, the galaxies, the gas, the dark matter, should act like a cosmic brake, pulling on the fabric of space-time and steadily decelerating its outward rush. The big question was simply whether there was enough matter to eventually halt the expansion altogether and pull everything back in a big crunch, or if it would just slow to a crawl. Then, in the late 1990s, two independent teams of astronomers made a discovery so shocking it would win them the Nobel Prize. They were using distant supernova specifically, a type called Aya supernova, which all explode with nearly the same intrinsic brightness as cosmic mile markers. By carefully measuring how bright these standard candles appeared from Earth, they could calculate their distance with great precision, and by measuring their redshift, they could determine how much the universe had stretched since the light left the exploding star. The results were not just surprising, they were mind-bending. The data revealed that the most distant supernovae were fainter than expected. This meant they were farther away than our models predicted. The stunning conclusion was that the expansion of the universe was not slowing down at all. In fact, it was speeding up. Some mysterious, repulsive force was stretching the cosmic fabric itself, pushing galaxies apart at an ever-increasing rate. This force was given a name that reflects our profound ignorance of its true nature: dark energy. Today, we understand that dark energy is the dominant component of the universe, making up a staggering 68% of all the mass energy content of the cosmos. That means it is more than twice as abundant as dark matter and billions of times more prevalent than all the visible matter in the stars and galaxies. Its primary effect is to exert a kind of negative pressure on the fabric of space-time, causing it to expand at an accelerating rate. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are the galaxies. If the bread dough is expanding, all the raisins move away from each other. Now, imagine the yeast in the dough suddenly gets more active, causing the loaf to expand faster and faster. That's the effect of dark energy. It's not that galaxies are moving through space away from each other. It's that the very space between them is being stretched, and that stretching is accelerating. This has profound and direct consequences for the cosmic skeleton we've been mapping. For billions of years, gravity was the undisputed master of the cosmos. tirelessly working to pull matter together into filaments, clusters, and nodes. But dark energy changes that narrative. It acts as a counterforce to gravity's attractive pull. On the very largest scales, the scale of the cosmic web itself, dark energy's repulsive effect is now winning. As the expansion accelerates, it begins to influence the growth and even the integrity of the large-scale structure. The delicate filaments of the cosmic web, those vast rivers of dark matter and galaxies, are being stretched ever thinner. The flow of gas along these filaments, which is the lifeblood for forming new stars in galaxies, will become more tenuous and may eventually be cut off entirely. Meanwhile, the great cosmic voids, those already empty deserts, are being stretched even larger and emptier at a faster rate as the accelerating expansion pulls their boundaries further apart. We can observe the fingerprints of dark energy not only in distant supernova, but also in the way the large-scale structure of the universe evolves over time. By measuring the clustering of galaxies at different cosmic epochs, astronomers can track how quickly structures have grown. Their findings confirm that the growth of galaxy clusters has slowed down over the last several billion years, precisely when dark energy is thought to have become the dominant force. It's as if the universe switched from a mode of construction to a mode of dilution. Gravity is still trying to build, but it's now fighting a losing battle against a pervasive force that is stretching the very canvas it's trying to build upon. Yet, for all we know about its effects, the true nature of dark energy remains one of the greatest mysteries in all of science. The leading hypothesis, originally proposed by Einstein himself and then discarded, is the cosmological constant, a constant energy density that is an inherent property of the vacuum of space itself. If this is correct, dark energy is immutable and will continue to accelerate the expansion forever. Other theories suggest it could be a dynamic field, nicknamed quintessence, that could change in strength over time. There are even more exotic ideas that suggest our theory of gravity itself, Einstein's general relativity, might need to be modified on the largest possible scales. We simply do not know. What we do know is that this mysterious force is the ultimate arbiter of the universe's fate. Its relentless acceleration doesn't just stretch the cosmic fabric, it writes the final chapter for the cosmic skeleton, determining whether the magnificent architecture we see today will endure, fade away, or be torn asunder. But the story of our cosmic web does not end with the structures we see today. It is a narrative still being written, a future already being shaped by the relentless, accelerating expansion driven by dark energy. To understand its ultimate fate, we must project our gaze forward across timescales that dwarf human history tens, even hundreds of billions of years into the future. The universe we know, with its glittering filaments and bustling galaxy clusters, is merely a single, fleeting frame in an epic movie that is still playing out. And the ending, according to our best models, is one of increasing isolation, darkness, and quiet dissolution. The primary driver of this future is the now dominant force of dark energy. For billions of years, gravity reigned supreme, patiently gathering matter into the magnificent architecture of the cosmic web. But that era of construction is drawing to a close. As the repulsive effect of dark energy continues to intensify, it will begin to stretch the very fabric of the web itself. The delicate threads of dark matter that connect galaxy clusters, those cosmic highways that have guided growth for eons, will be pulled taut. Simulations show that over tens of billions of years, these filaments will become increasingly tenuous, stretched by the accelerating expansion until they eventually snap. The great metropolitan clusters, once connected by these vibrant trade routes, will become isolated islands in an ever-widening sea of nothingness. They will be cut off from the flows of gas that have sustained star formation for so long, their vibrant galactic cities slowly beginning to dim. This isolation triggers a cascade of consequences. Within the isolated galaxy clusters, star formation will not cease immediately. There will be a final, glorious burst of activity as the last reservoirs of gas within the clusters collapse to form stars. But without any fresh fuel arriving from the now severed filaments, this is a finite resource. One by one, the stellar nurseries will fall silent. The massive, brilliant blue stars that lie fast and die young will be the first to go, exploding as supernova and leaving behind neutron stars and black holes. Eventually, only the longer-lived, smaller red stars will remain, burning through their fuel at a much slower, more frugal pace. Over hundreds of billions of years, even these faint embers will eventually flicker out. The galaxies, once vibrant swirls of blue, white, and gold, will fade to a uniform, dull red, and then, ultimately, to black. The universe will enter what astronomers call the degenerate era, a time dominated by the cold, dark remnants of stars, white dwarfs, neutron stars, and black holes, slowly orbiting each other in the darkness. The expansion itself will continue to accelerate, leading to a profoundly lonely and empty cosmos. Distant galaxies that are currently visible to our most powerful telescopes will have been pushed so far away by the stretching of space that their light, no matter how long it travels, will never be able to reach what remains of our local galaxy group. The universe beyond our immediate neighborhood will effectively disappear from view, receding over a cosmic horizon. The night sky for any hypothetical observers in that far future, perhaps orbiting a cold, dead star, would be utterly black and empty, devoid of any external galaxies. The evidence for a Big Bang, the cosmic microwave background radiation, will have been stretched to such long wavelengths that it becomes undetectable. The universe will have erased the forensic evidence of its own origin. This long-term evolution from a hot, dense beginning to a cold, dark, and empty end is known as the heat death scenario or the Big Freeze. It paints a picture of a universe that is not only expanding but also effectively dying, its useful energy exhausted and its structure dissolved. This fate underscores the profoundly transient nature of everything we see in the cosmos today. The magnificent cosmic skeleton we are working so hard to map is not a permanent fixture. It is a temporary pattern, a beautiful and complex phase in the universe's life cycle that emerges from the battle between gravity and dark energy, only to be eventually erased by the victor. Our current maps are therefore not just a snapshot of how the universe is, but a precious record of how it was at a specific, vibrant moment in its multi-trillion-year history. Understanding this distant fate is not merely an exercise in melancholy speculation. It is a crucial part of cosmology, intimately connected to our understanding of the universe's beginning. The same dark energy that dictates the future end also influences how structures formed in the past. By modeling how the cosmic web evolves forward in time, we can test our theories of gravity and the nature of dark energy, refining our models of the initial conditions from which it all sprang. The ultimate fate of the cosmic skeleton is written into its initial blueprint, and by studying one, we learn more about the other. This grand narrative, from quantum seed to cold, dark silence, connects the invisible architecture to the deepest questions about the nature of time, existence, and the ultimate destiny of all things. It's easy to dismiss the quest to map the cosmic web as a purely abstract pursuit, a magnificent intellectual exercise that exists in a realm far removed from our daily concerns. What tangible difference does it make, one might ask, to know the shape of dark matter filaments billions of light years away? The beautiful and perhaps surprising truth is that this grand endeavor to understand the universe's hidden architecture consistently spins off innovations that ripple back to Earth, quietly improving our technology, sharpening our computational tools, and even refining our perspective on the very planet we call home. This isn't just science for science's sake, it's a foundational investment in our future. At its heart, cosmology is an extreme testing ground for the laws of physics. To model the cosmic web, we must push our understanding of gravity, particle interactions, and the behavior of matter and energy under the most extreme conditions conceivable. This relentless pursuit to make our simulations match the observations forces us to refine the most fundamental theories we have. And history has shown us time and again that breakthroughs in fundamental physics have a remarkable habit of sparking revolutionary technologies. The development of quantum mechanics, for instance, was driven by a desire to understand the atom, but it ultimately gave us the transistor, the laser, and the entire field of modern computing. In the same way, a deeper understanding of gravity or a potential discovery related to the nature of dark matter could unlock paradigms we can scarcely imagine today, perhaps new forms of energy generation, radically new propulsion systems for spacecraft, or entirely novel materials with incredible properties. The GPS in your phone, for example, only works because it must account for the subtle effects of general relativity. The satellite's clocks run at a different rate than those on Earth. Mapping the cosmos requires us to understand relativity and gravity with even greater precision, which could one day lead to navigation systems of astounding accuracy, both on Earth and for voyages between the stars. Perhaps the most direct and widespread practical application lies not in the cosmic maps themselves, but in the tools we must invent to create them. The challenge of processing the astronomical amount of data from sky surveys like the Sloan Digital Sky Survey or the upcoming Legacy Survey of Space and Time at the Vera Rubin Observatory has driven monumental advances in data science, image processing, and machine learning. Astronomers, faced with billions of galaxies to classify and measure, were among the early pioneers in developing machine learning algorithms to automate this incredibly complex task. The techniques they created to identify faint, distant galaxies hidden in noisy data, or to find subtle patterns within immense datasets, are now being adapted for use in fields like medical research, where similar algorithms can help diagnose diseases from medical scans by recognizing patterns invisible to the human eye. The complex computational frameworks built to run universe-spanning simulations are now used to model other incredibly complex systems, such as global climate patterns, the flow of traffic in megacities, or the dynamics of financial markets. The quest to understand the cosmic web has, in effect, gifted us a powerful new lens through which to analyze and solve some of the most intricate problems right here on Earth. Furthermore, this grand cosmic perspective provides a crucial, long-term context for our own existence. By refining our models of the universe's expansion and the evolution of large-scale structure, we are essentially calibrating the ultimate clock and mapping the ultimate geography of reality. This knowledge is the bedrock of any future aspiration for long-duration, large-scale space exploration. If humanity ever hopes to venture beyond our solar system, we will need a profound understanding of the structure of the local universe, the distribution of resources within it, and the forces that will shape its future. While it may seem like the stuff of science fiction, this cosmological mapping is the first, essential step toward turning that fiction into fact. It allows us to think on timescales of billions of years, which in turn fosters a more responsible, sustainable perspective on the management of resources and the future of our own civilization. It teaches us that we exist within a dynamic, evolving system, a lesson that is profoundly relevant as we navigate the changes we are bringing about on our own planet. This powerful connection between the seemingly abstract pursuit of cosmic knowledge and tangible, earthly benefits demonstrates that exploring the hidden skeleton of the universe is far from an esoteric indulgence. It is an endeavor that sharpens our intellect, inspires our technology, and ultimately deepens our understanding of our place within an interconnected reality. The tools forged in the fires of cosmological inquiry are already helping to build a better world, proving that by reaching for the farthest reaches of the cosmos, we often find the keys to unlocking new possibilities right here at home. Contemplating our place within this grand cosmic architecture can be a profoundly humbling experience. We find ourselves on a small, rocky planet orbiting an average star, which itself is just one of hundreds of billions in our galaxy. And our galaxy, it is a single speck, one tiny luminous point strung along a vast, dark filament of the cosmic web, one among countless others flowing toward the great attractor of the Laniakea supercluster. In the sheer physical scale of the universe, we are inconsequentially small, a fleeting whisper in a cosmos that spans billions of light years and billions of years. This perspective, forged by our own scientific discoveries, directly challenges any notion that we are the central characters in the universe's story. It dismantles anthropocentric views, replacing them with a powerful sense of awe and a deep, grounding humility. We are not the center of creation. We are participants in an immense, ongoing process that is vastly older and grander than ourselves. Yet there is a breathtaking paradox at the heart of this humility. We are these tiny, seemingly insignificant specks of star stuff, and yet we possess the extraordinary capacity to perceive, to question, and to understand the very architecture that contains us. The human mind, through the tools of science and mathematics, has been able to deduce the existence of dark matter, to trace the outlines of billion light-year filaments, and to peer back to the very first light of the universe. We have uncovered the hidden skeleton of reality itself. This ability transforms our story from one of mere smallness to one of profound significance. Our consciousness allows the universe to, in a very real sense, become aware of itself. We are the universe's way of looking back at its own beautiful and intricate design, of marveling at its own history and contemplating its own fate. This transforms the scientific endeavor from a cold, detached collection of facts into a deeply meaningful journey of self-discovery, a way for us to understand our own origins and our connection to the cosmos at large. This revelation of a universe governed by elegant, mathematical laws and predictable patterns also stirs ancient philosophical debates with new urgency. The cosmic web, with its structures evolving over billions of years according to the strict laws of physics, presents a vision of a universe that appears deeply deterministic. From the quantum seeds of inflation to the formation of galaxies along dark matter highways, every step seems to follow an unbreakable chain of cause and effect. This raises profound questions about our own place in this causal web. If the universe operates on such predictable principles, where does that leave human free will? Are our choices and consciousness merely the products of particles obeying physical laws, a complex but predetermined dance of matter and energy? Or does our emergent consciousness represent something genuinely novel, a new layer of complexity that can exert its own influence on the world? There are no easy answers, but the map of the cosmic skeleton forces us to confront these questions with a new depth and clarity, blending physics with philosophy in the most fundamental way. And of course, gazing out at this immense and structured universe inevitably leads us to wonder about who else might be out there looking back. the cosmic web isn't just a structure of matter, it is a potential architecture for life. Those same filaments that channel gas to feed galaxies also deliver the essential ingredients for planets and biology. If the laws of physics are universal and the building blocks of life are common, then the sheer number of planets orbiting stars within this web-like structure makes the existence of other life forms seem not just possible but probable. The search for extraterrestrial intelligence becomes a search for other conscious nodes within the network, other points where the universe has become self-aware. This possibility adds another layer of meaning to our cartography of the cosmos. We are not just mapping empty space, we are potentially charting the highways and habitations of other civilizations, making the philosophical quest to understand our place also a practical preparation for a future where we might not be alone. Ultimately, these philosophical musings do not distract from the science. They deepen its impact and enrich our appreciation for the cosmos. They remind us that every data point from a telescope, every simulation of dark matter, is more than just a number. It is a piece of a larger story about existence, consciousness, and our connection to the universe. This journey to map the hidden skeleton is, therefore, one of the most profoundly human endeavors we can undertake. It satisfies our innate curiosity, humbles our ego, and inspires a sense of wonder that has guided explorers and thinkers for millennia. As we continue to grapple with these immense questions, our drive to find answers propels us toward the next horizon of discovery, eager to see what new tools and missions will reveal about the cosmic architecture we call home. The pace of discovery is about to accelerate in ways that were once unimaginable, as a new generation of cosmic cartographers prepares to deploy its tools. Leading this charge is the European Space Agency's Euclid Space Telescope, an instrument specifically designed to tackle the universe's greatest mysteries. Unlike telescopes that focus on small, deep fields, Euclid is a wide-eyed surveyor of the heavens, engineered to map the three-dimensional distribution of up to 2 billion galaxies across an astounding one-third of the entire sky. Its mission is to create the most extensive and precise chart of the cosmic web ever assembled, measuring the shapes and distances of these galaxies with exquisite accuracy. But it's not just creating a map, it's using that map as a diagnostic tool. By observing how the web has evolved over the last 10 billion years, Euclid will probe the nature of both dark matter and dark energy. It will trace the dark matter directly through the subtle distortions of gravitational lensing, watching how its mass warps the light from background galaxies. Simultaneously, by measuring the precise distances to galaxies, it will track how the expansion rate of the universe has changed over cosmic time, providing our most stringent test yet for the properties of the enigmatic dark energy that drives it. This single mission is poised to transform our understanding of the invisible forces that have shaped everything we see. On the ground, a complementary revolution is underway at the Vera Rubin Observatory in Chile. This facility is built around the largest digital camera ever constructed for astronomy, a behemoth with a resolution of over 3.2 gigapixels. For 10 years, its legacy survey of space and time will repeatedly scan the entire southern sky, not just once, but over and over, creating an unprecedented cinematic view of the cosmos. This isn't a static picture, it's a dynamic movie that will capture changes over time. It will detect billions of new galaxies, but more importantly, it will track how their positions and properties shift. This allows astronomers to witness the cosmic web in motion, to see the gravitational flows that pull galaxies along filaments and into clusters. The survey will also catalog countless stellar explosions called supernova, using them as standard candles to independently measure the universe's expansion and provide a cross-check for Euclid's findings. The sheer volume of data will be staggering, expected to reach hundreds of petabytes, and it will require new generations of algorithms and supercomputers just to process the flood of information. This ground-based eye on the sky will work in powerful synergy with Euclid's space-based perspective, creating a multi-faceted and multi-wavelength atlas of the hidden skeleton. Yet, even the most powerful telescopes only provide a snapshot of reality. To truly understand the physics that governs the evolution of these vast structures, we must turn to the virtual universe. The next frontier in simulation is being powered by the dual engines of artificial intelligence and the nascent potential of quantum computing. Traditional n-body simulations, while incredibly powerful, are computationally exhausting, requiring millions of CPU hours on the world's largest supercomputers. AI is now revolutionizing this process. Scientists are training machine learning models on the simulations we already have, teaching neural networks the complex rules of gravitational physics, gas dynamics, and star formation. Once trained, these AI programs can generate incredibly high-resolution mock universes in a fraction of the time, allowing researchers to test thousands of different cosmological models and parameters almost instantaneously. This is like moving from hand-drawing maps to having an AI cartographer that can instantly generate every possible variation of a landscape. Looking further ahead, quantum computing offers a mind-bending possibility. The behavior of dark matter and the fundamental forces that shape the web may involve quantum-level interactions that are notoriously difficult for classical computers to model. Quantum computers operating on the principles of superposition and entanglement could potentially simulate these processes with a natural ease, unlocking a deeper, more fundamental level of understanding of how the cosmic skeleton is built from the ground up. Together, this trinity of tools, the space telescope, the ground-based observatory, and the advanced digital universe, forms an integrated campaign to answer the most profound questions in cosmology. They will precisely measure the lumpiness of dark matter, determining if it is cold, warm, or something else entirely, which will tell us how the finest strands of the web first formed. They will constrain the equation of state of dark energy, revealing whether it is a constant force or something that varies over time, which will dictate the ultimate fate of all cosmic structure. These missions will search for primordial ripples in space-time itself, gravitational waves from the inflation era, which could be imprinted on the patterns of galaxies we see today. The anticipation within the scientific community is electric, because we are on the verge of moving from an era of discovery to an era of precision. We are no longer just asking if the cosmic web exists. We are preparing to take its detailed measurements, to understand its composition, and to diagnose its health. This isn't the end of the journey. It is the beginning of its most exciting chapter, where the hidden architecture of the cosmos will be revealed in stunning, unprecedented detail. For all the breathtaking progress we've made in mapping the cosmos, the most exciting part of the journey lies in the profound questions that remain wide open. Each new map we create doesn't just provide answers. It reveals deeper layers of mystery, reminding us that the universe is far stranger and more wonderful than we ever imagined. The true nature of the two titans that govern our universe, dark matter and dark energy, remains perhaps the greatest puzzle in all of physics. We see dark matter's gravitational handiwork everywhere, sculpting the cosmic web and holding galaxies together, yet we still have no idea what it actually is. Is it a sea of exotic, undiscovered particles, perhaps trillions of times lighter than an electron, streaming through our laboratories right now without a trace? Or could our understanding of gravity itself be incomplete on the largest scales, requiring a fundamental rewrite of the laws set down by Newton and Einstein. The answer is somewhere out there in the dark, and its discovery would revolutionize our conception of reality itself. Equally baffling is the force we call dark energy, the mysterious engine driving the universe's accelerating expansion. Is it a constant property of the vacuum of space itself, as Einstein's cosmological constant suggested, or is it a dynamic field that has changed in strength over the universe's history? This isn't just an academic distinction. The answer dictates the cosmos's ultimate fate. If dark energy is constant, the universe will continue its slow, cold expansion into eternity. But if it strengthens over time, it could lead to a far more dramatic end, a Big Rip, where the fabric of space-time itself is torn apart, shredding galaxies, planets, and even atoms in a final, catastrophic instant. We are essentially trying to diagnose the engine of the universe while only being able to observe its exhaust, and the next generation of telescopes is our best hope for a clearer reading. Beyond these known unknowns, the cosmic skeleton might be woven with structures we have only theorized about. Could the early universe have forged incredibly dense, unimaginably thin defects in space-time called cosmic strings? These hypothetical relics, thinner than a proton but stretching across the entire universe, would possess immense mass and would warp the space around them so severely that they might create double images of distant galaxies or leave telltale ripples in the fabric of space-time known as gravitational waves. Their discovery would be a direct window into the universe's first moments, a fossil from a time of unimaginable energy. Furthermore, our current maps show a universe that is, on the largest scales, remarkably smooth and homogeneous, a fundamental assumption of cosmology called the cosmological principle. Yet, tantalizing anomalies challenge this neat picture. The most famous is the mysterious cold spot in the cosmic microwave background, a region of space far colder than our models can easily explain. Is it a statistical fluke, a mere trick of the light? Or could it be evidence of a collision with another universe in the vast multiverse, or perhaps a giant supervoid so vast it defies our understanding of structure formation? These irregularities are the cosmic equivalents of a detective finding a single, unexplained fingerprint at a crime scene. They hint that there may be entire chapters of physics we haven't even begun to write. These are not failures of our science, they are its lifeblood. Each unanswered question is a frontier, a beacon calling researchers to develop new theories, design ingenious experiments, and build even more powerful telescopes. The existence of these mysteries is what makes cosmology a living, breathing field of discovery rather than a dusty book of completed answers. It is a powerful reminder that our map of the hidden skeleton is still a work in progress, a rough sketch that future generations will fill in with brilliant detail and undoubtedly with stunning surprises that we cannot yet foresee. This embrace of the unknown is the very essence of scientific curiosity, a driving force that ensures the grand endeavor of cosmic cartography will continue to captivate and inspire us for centuries to come. Behind every great leap in our understanding of the cosmos stand the brilliant and determined individuals who dared to ask new questions and see the universe differently. These are not just names in textbooks. They are pioneers who dedicated their lives to peeling back the layers of reality, often facing skepticism and working for decades before their insights were recognized. Their stories are a powerful reminder that science is a profoundly human endeavor, built on curiosity, perseverance, and a shared passion for discovery. To truly appreciate the map of the hidden skeleton, we must celebrate the cartographers who first traced its outlines. Consider the work of Vera Rubin in the 1960s and 70s. At a time when women were a rarity in observatories, she was meticulously measuring the rotation speeds of stars within distant galaxies. The prevailing theory suggested that stars at the outer edges of a spiral galaxy, far from the central bulge of mass, should orbit more slowly, just as Pluto moves more sluggishly around the Sun than Earth does. But her data told a different and astonishing story. She found that stars on the outskirts of galaxies were whipping around just as fast as those near the center. This meant there had to be a tremendous amount of invisible mass, far more than the visible stars and gas, exerting a gravitational pull to keep those stars from flying off into space. Her galaxy rotation curves became one of the most compelling lines of evidence for the existence of dark matter. Yet for years, her groundbreaking work was met with resistance and dismissal from a largely male-dominated field. Her perseverance in the face of this skepticism fundamentally altered the course of cosmology, forcing the entire scientific community to confront the reality that most of the universe's matter was completely invisible to us. Around the same time, on the other side of the world in the Soviet Union, an Estonian astronomer named John Einasto was leading a team that reached a similar, monumental conclusion. Using painstaking measurements of galaxy distances and motions, they independently discovered that the universe's mass budget didn't add up. But Einasto's group took the idea a revolutionary step further. They began to see that this dark matter wasn't just a halo around individual galaxies. It was organized on a scale so vast it defied imagination. They were among the very first to propose that galaxies were not scattered randomly, but were instead connected by a vast, web-like structure of dark matter, a concept they called the cosmic web or supercluster void network. This was a radical departure from the prevailing view of a fairly uniform universe. Einasto and his colleagues were essentially the first to propose the existence of the invisible architecture we've been exploring, envisioning the grand skeleton of the cosmos long before our telescopes or computers were powerful enough to confirm it. The legacy of these foundational pioneers is carried forward today by massive, international collaborations that represent the next chapter of cosmic exploration. The Sloan Digital Sky Survey, initiated in the late 1990s, wasn't the work of a single individual but of hundreds of scientists and engineers working in concert. Their goal was audacious: to create a comprehensive three-dimensional map of a huge portion of the universe. Using a specialized telescope equipped with a genius device that could capture the spectra of 600 galaxies at once, they began methodically charting the heavens. The project's directors and lead researchers guided this colossal effort, and the result was a revelation. The SDSS map showed the large-scale structure of the universe in stunning, irrefutable detail, revealing the filamentary walls and giant voids that Einasto had predicted. It provided the first truly extensive visual proof of the cosmic web, turning a theoretical idea into an observed reality, and gifting every astronomer on the planet with an unprecedented dataset to explore. Similarly, the Planck space mission, a project of the European Space Agency, was the culmination of work by thousands of individuals over decades. The scientists and engineers who designed its incredibly sensitive instruments aimed to create the sharpest possible image of the universe's oldest light, the cosmic microwave background. Their meticulous work allowed us to see the faintest ripples and imperfections in this primordial radiation, which are the direct blueprints for the cosmic web. The precise measurements from the Planck satellite confirmed the standard model of cosmology with remarkable accuracy, telling us exactly how much dark matter and dark energy the universe contains and validating the theoretical framework that grew from the early work of pioneers like Rubin and Einasto. These modern projects highlight a crucial evolution in science. While the romantic image of a lone genius making a discovery still exists, the biggest questions now require global teamwork, immense technological resources, and a shared commitment to a goal that no single person could ever achieve alone. The story of cosmic mapping is a testament to human curiosity and tenacity. It's a narrative that spans generations, from the initial, stubbornly collected data points that challenged established dogma, to the vast digital sky surveys that now define modern astronomy. These pioneers, both past and present, teach us that profound discoveries often begin with a careful look at something that doesn't quite make sense, and the courage to trust the data even when it leads to a startling and unfamiliar new world. By putting a human face on this grand quest, we see that science is not a cold, impersonal collection of facts, but a slow and steady journey of understanding, built by people who dared to map the invisible. But what if I told you that you don't need a PhD or access to $1 billion telescope to contribute to this grand endeavor? That you, right now from your own home, could play a direct role in mapping the hidden skeleton of the cosmos. This is the incredible power of citizen science, a movement that is fundamentally democratizing the process of discovery and opening the doors of cosmic cartography to everyone. For centuries, astronomy was the domain of a select few. But the digital age has transformed it into a collaborative global project where anyone with curiosity and an internet connection can make a genuine contribution to our understanding of the universe. Platforms like Zooniverse serve as the gateway to this new frontier. This online portal hosts dozens of active research projects, many of them in astrophysics, where scientists are desperate for the one thing supercomputers still struggle with: the human brain's remarkable ability to recognize patterns and anomalies. One of the most famous and impactful projects is Galaxies. The challenge was simple but monumental. Astronomers had images of nearly 1 million galaxies from robotic telescope surveys, but they needed each one to be classified by shape. Is it a spiral, an elliptical? Is it merging with another galaxy? This is a task that is trivial for a human but incredibly difficult to code for a machine. So they asked for help. The response was breathtaking. Within the first year, over 50 million classifications were made by more than 150,000 volunteers. This wasn't just busy work. This massive human-powered analysis led to the discovery of entirely new classes of astronomical objects, like the now famous green pea galaxies, and provided the crucial data that helped confirm how galaxies align within the cosmic web's filaments. Your ability to look at an image and say, "That looks odd," is a unique and invaluable scientific instrument. The advantages of this human-in-the-loop approach are profound. While algorithms are excellent at processing vast amounts of data quickly, they can be blindsided by things they weren't specifically programmed to find. They might perfectly classify standard spiral galaxies, but completely miss a strange, warped galaxy that's being gravitationally lensed by an unseen clump of dark matter. A human volunteer, however, might spot that anomaly instantly and flag it for professional astronomers to investigate. This synergy is powerful. The citizen scientists act as a massive, distributed anomaly detection network, sifting through the haystacks of data to find the most interesting needles for experts to then examine with their most powerful tools. It's a perfect partnership that leverages the unique strengths of both people and machines. Beyond classification, a world of other opportunities exists. Projects like Radio Galaxy Zoo ask volunteers to trace the colossal jets erupting from supermassive black holes across different wavelengths of light. Others, like Planet Hunters, have allowed volunteers to sift through data from the Kepler Space Telescope to look for the telltale dips in starlight caused by orbiting exoplanets, leading to numerous discoveries that automated routines had missed. There are even projects focused on our own cosmic backyard, mapping the moon with NASA or searching for distant objects in the Kuiper belt. Each of these tasks contributes a small piece to the enormous puzzle of the cosmic web, helping to refine our maps of where matter is located and how it behaves. This engagement goes far beyond just contributing data points. Participating in these projects creates a profound and personal shift in perspective. When you spend an evening classifying galaxies, you are no longer just a passive observer of science. You become an active participant in its creation. The distant, abstract universe of documentaries suddenly becomes a tangible place that you are helping to measure and understand. You develop an intimate connection to the data, remembering the peculiar galaxy you found or the beautiful merger you flagged. This process transforms the cosmos from something you learn about into something you do, fostering a deeper sense of connection and ownership over our collective understanding. Educational resources, online forums, and even live chats with researchers associated with these projects further enrich the experience, creating a genuine global community of learners and discoverers. This democratization of discovery is one of the most beautiful aspects of modern science. It shatters the old model of the isolated genius and replaces it with a collaborative, inclusive effort that spans the globe. It empowers individuals, from students to retirees, to know that they have directly contributed to humanity's grandest quest, the quest to understand our place in the universe. Your curiosity becomes a legitimate tool of exploration, and in helping to trace the invisible architecture of space, you weave your own thread into the great tapestry of human knowledge. This collective effort, where every participant plays a part, naturally leads us to consider the broader responsibilities that come with this newfound power of discovery. Yet as we reach for the stars and chart the invisible architecture of the cosmos, we must also pause to look inward, to consider the profound ethical responsibilities that accompany such profound discovery. This journey is not merely a technical challenge. It is a deeply human one, raising questions that strike at the very heart of our values, our priorities, and our shared future on this pale blue dot. The first and perhaps most immediate ethical consideration is one of resource allocation. We live in a world of finite means, where pressing earthly problems, climate change, poverty, disease, and conflict demand immense investment and attention. It is a valid and necessary question to ask: how can we justify spending billions on space telescopes and supercomputer simulations when there is so much suffering right here at home? This is not a question to be dismissed, but to be engaged with thoughtfully. The answer lies not in choosing one over the other, but in recognizing the deep and often surprising interconnectedness between cosmic exploration and terrestrial benefit. The technological spin-offs from space research, from medical imaging to water purification systems to global communication networks, have repeatedly yielded tangible improvements in human welfare. More fundamentally, the pursuit of knowledge is a core part of what it means to be human. It fuels our innovation, inspires our youth, and provides a unifying goal that transcends national borders. The challenge, then, is not to stop looking up, but to ensure that the benefits of looking up are distributed equitably, that the knowledge and technology we gain are used to lift all of humanity, not just a privileged few. This demands international cooperation and open data policies, ensuring that a child in a developing nation has the same access to the data from the James Webb Space Telescope as a researcher at the most prestigious university, fostering a truly global scientific community. Beyond the practicalities of funding lies an even deeper ethical layer: the potential impact of our discoveries on humanity's sense of self and our various belief systems. Throughout history, cosmological revelations have repeatedly challenged our anthropocentric view of the universe. we learned that Earth is not the center of the solar system, that our Sun is a typical star in a vast galaxy, and that our galaxy is but one of trillions. Each discovery has humbled us, displacing us from a privileged position at the center of creation. As we now map the cosmic web and probe the nature of dark matter and dark energy, we edge closer to answers for the ultimate questions of our origin and fate. What happens if we discover conclusive evidence for a multiverse, or if we finally identify the particle that makes up dark matter, revealing a fundamental layer of reality previously unknown? Such discoveries could have seismic effects on philosophical and religious worldviews that have provided meaning and comfort for millennia. The ethical approach here is not to wield science as a weapon against faith, but to engage in a respectful and humble dialogue. Science offers a powerful methodology for understanding the mechanics of the universe, but it does not inherently provide a framework for meaning, purpose, or morality. A responsible scientific enterprise acknowledges its limits and respects the different ways in which people find significance in the cosmos, recognizing that the awe inspired by a spiral galaxy and the awe inspired by a sacred text can be two different, equally valid expressions of the human spirit. This leads to the final and perhaps most important ethical pillar, the cultivation of humility. The sheer scale and mystery of the cosmic skeleton should serve as a perpetual antidote to arrogance. For every answer we find, a dozen new questions emerge. We have mapped the cosmic web, yet we do not know what 95% of the universe is made of. We are like explorers who have drawn the coastlines of a continent, but have no idea what lies in its vast, uncharted interior. This vast unknown should instill in us not a sense of frustration, but a profound sense of wonder and a deep respect for the limits of our current understanding. A responsible exploration of the cosmos is conducted with this humility at its core. It means we must avoid the trap of scientism, the belief that science is the only valid way of understanding existence. It means we must proceed with caution when considering technologies with existential implications, from advanced artificial intelligence to potential planetary engineering. And it means we must always remember that the universe does not owe us answers. Every glimpse we get into its hidden workings is a privilege. This humble, respectful approach transforms the scientific endeavor from a cold, calculated conquest into a shared, wondrous journey, one that acknowledges our tiny place in the grand scheme while simultaneously celebrating our incredible capacity to comprehend it. This ethical framework ensures that as we continue to map the cosmos, we do so not just as scientists, but as thoughtful, responsible citizens of a universe far grander than we can fully imagine. So let's bring it all together. We've journeyed through the invisible architecture of the cosmos, and the picture that emerges is one of breathtaking elegance and profound complexity. It all begins with the cosmic web itself, the grand, large-scale structure of the universe. This isn't a random scattering of galaxies, but a highly organized network, a vast skeleton of filaments and voids that forms the fundamental framework for everything we see. This web wasn't built from the visible stars and gas, but from the gravitational influence of dark matter, the unseen scaffolding that comprises the majority of the universe's mass and provides the essential blueprint. It is this mysterious substance, detected only by its gravitational pull, that carved out the contours of this architecture, creating the gravitational wells and highways that would guide the formation of the visible universe. And guide it did. We saw how galaxies are not isolated islands but are strung along these cosmic filaments like pearls on a string, forming primarily at the dense intersections where dark matter is most concentrated. These filaments act as cosmic rivers, channeling gas and entire galaxies over billions of years, fueling star formation and delivering material to the massive clusters that sit at the nodes. But the story isn't just about the dense regions. The cosmic voids, those vast, empty deserts that make up most of the universe's volume, play an equally crucial role. Their repulsive gravity and accelerated expansion help to define the filaments and shape the overall dynamics of the web, creating a dynamic tension between the dense and the empty. The master sculptor behind this entire process is gravity. Acting on the tiny, quantum fluctuations imprinted in the first moments after the Big Bang, fluctuations we can still see in the cosmic microwave background, gravity spent billions of years amplifying those minuscule seeds into the magnificent cosmic web we observe today. This process of growth, guided by Einstein's theory of general relativity, is a story of relentless attraction, of matter being pulled into the patterns we now map. And map it we do using an incredible suite of tools. Supercomputer simulations allow us to run the universe's evolution forward and backward in time, testing our theories of dark matter and gravity. Meanwhile, powerful telescopes, from the Hubble and James Webb Space Observatories to massive ground-based surveys like the Sloan Digital Sky Survey, provide the real-world data. They chart the positions of millions of galaxies, detect the faint X-ray glow of hot gas in filaments, and use the phenomenon of gravitational lensing to literally weigh the invisible dark matter. This powerful combination of digital and observational cartography has allowed us to create increasingly detailed maps of this hidden skeleton. Yet, just as we began to understand gravity's constructive role, we encountered its counterforce, dark energy. This mysterious repulsive energy, causing the expansion of the universe to accelerate, is now stretching the cosmic fabric itself. It is thinning the filaments, enlarging the voids, and ultimately dictating the long-term fate of the cosmic web, leading to a future of isolation and darkness. This discovery reminds us that the cosmos is not static but is a dynamic, evolving system, and our current maps are but a snapshot in its grand multi-billion-year narrative. This entire endeavor is pushed forward by key discoveries that have illuminated the hidden framework, from the shocking emptiness of the Boötes void to the definition of our home supercluster, Laniakea. It is driven by pioneers who challenged paradigms and by citizens around the world who now contribute to real research from their own homes. And the implications of this knowledge ripple outward, improving technology here on Earth, refining our models of physics, and forcing us to confront deep philosophical questions about our place within this vast, structured, and evolving universe. This invisible skeleton, therefore, is more than just a cosmic curiosity. It is the fundamental blueprint of reality, connecting the universe's explosive beginning to its distant future, and revealing our own existence as a small but conscious part of an unimaginably grand design. Think about the last time you truly looked up at a night sky away from the city lights. That overwhelming sense of awe, the sheer number of stars. It's a powerful experience, but it's also one that can feel random, even chaotic. Now, reimagine that same view with the knowledge of the cosmic web. Those aren't just random points of light anymore. Each one is a marker, a luminous signpost tracing out the contours of something vastly larger and mostly hidden. That bright star might be part of our local galactic arm, while that faint smudge could be an entire galaxy millions of light years away, and both are following the invisible gravitational currents of dark matter filaments, like leaves floating on the surface of a river whose depths and currents you've just learned to sense. This is the profound shift in perception that this knowledge brings. It's the difference between looking at a scattering of iron filings on a table and suddenly understanding that they are aligned by the presence of a powerful magnet you cannot see. The universe transforms from a chaotic scattering into a place of immense order and intricate connection. This new lens doesn't diminish the beauty, it deepens it, adding layers of context and meaning that make the cosmos feel more elegant, more structured, and far more fascinating. This shift does something else too. It fundamentally changes our relationship with science itself. The process of discovery, from Vera Rubin's meticulous measurements to the jaw-dropping data from the James Webb Space Telescope, is no longer a distant, abstract activity performed by people in lab coats. It becomes a shared human story, a collective effort to understand our home, knowing that the faint light from a distant quasar has traveled for billions of years, warping around invisible masses just to bring us a message about the structure of space, turns astronomy from a subject into a saga. It fosters a deeper, more personal appreciation for the scientific endeavor, not as a cold collection of facts, but as the most powerful tool we have for decoding the mysteries of our existence. This understanding can reignite a childlike sense of curiosity and wonder that often gets buried in daily life, prompting us to ask bigger questions and look for the hidden patterns not just in the stars, but in the world around us. With this new perspective comes a powerful sense of context for our own existence, a cosmic perspective that is both humbling and empowering. We realize that our planet, our solar system, and our entire galaxy are not at the center of everything but are participants in a much grander scheme. We are embedded within this evolving architecture, our local group of galaxies flowing along a specific filament toward the great attractor in the Laniakea supercluster. This knowledge can be a profound antidote to a narrow, self-centered worldview. It instills a sense of humility, recognizing our tiny place in the vastness of space and time. Yet, paradoxically, it is also incredibly empowering. That same insignificant speck humanity has managed to uncover these secrets. We have deduced the existence of dark matter, mapped the ancient light of the Big Bang, and pieced together the story of the cosmic web. This means we are not just passive inhabitants of this structure, we are its conscious agents, the universe's way of becoming aware of its own magnificent design. This transformed perception is far more than just an interesting intellectual exercise. It's a catalyst. Knowing we are part of such a beautiful and mysterious system can inspire creativity in art, music, and literature, providing a new wellspring of metaphor and imagery that reflects our updated understanding of reality. It can drive innovation in technology as we strive to build better tools to see further and map more precisely, leading to advancements that often find unexpected applications in medicine, computing, and global communication. Perhaps most importantly, it can foster a greater commitment to exploration and stewardship, a desire to protect our fragile planet as we learn it is a rare and precious oasis in the vast cosmic desert, and a renewed passion to continue venturing out, both physically and intellectually, into the unknown. This outlook isn't an ending, it's an invitation to a lifelong conversation with the universe, a starting point from which we can continue to learn, explore, and find our place within the grand, invisible architecture of it all. If this journey through the cosmic web has ignited a spark of curiosity, the good news is that your exploration doesn't have to end here. There is a universe of incredible resources waiting for you, designed to take you deeper into these mysteries from the comfort of your own home. For those who love the tactile feel of a book and the deep dive it provides, I highly recommend starting with Richard Gott's The Cosmic Web. It's a masterful work that reads like a detective story, chronicling the scientific journey to discover the large-scale structure of the universe, written by one of the pioneering astronomers who helped map it. For a broader and utterly breathtaking visual journey through all of cosmology, Neil deGrasse Tyson's Cosmos, A Space-Time Odyssey is a modern classic. This documentary series doesn't just present facts, it weaves science with history and philosophy, creating a truly inspirational experience that makes you feel connected to the cosmos in a profound way. The beauty of our digital age is that you can literally sit in on world-class university courses without leaving your house. Platforms like Coursera and edX offer fantastic courses on cosmology and astrophysics from institutions like Caltech, the University of Chicago, and Australian National University. These aren't just watered-down overviews, they are serious, structured classes that will give you a firm grounding in the mathematics and physics behind everything we've discussed, from general relativity to dark matter. If you prefer to stay on the cutting edge of discovery, make the websites of NASA and the European Space Agency your regular stopping points. Their news sections are constantly updated with press releases, stunning images from the James Webb Space Telescope, and detailed articles explaining the latest findings in clear, accessible language. They are the primary sources, giving you the information straight from the teams who are actually doing the exploring. For learning on the go, the world of podcasts is an absolute treasure trove. Shows like Star Talk with Neil deGrasse Tyson blend science and pop culture with fantastic interviews, while more technical ones like the Supermassive podcast from the Royal Astronomical Society dive into the nitty-gritty details of recent research papers. And of course, YouTube is home to an entire ecosystem of brilliant educators and animators who specialize in making the most complex ideas in astrophysics visually intuitive and wildly entertaining. Channels like PBS Space-Time, Kurzgesagt, and Dr. Becky offer everything from short, explainer animations to deep, hour-long lectures that can satisfy any level of interest. The key is to find the format that you enjoy the most, because when learning is a pleasure, it stops being a chore and becomes a lifelong adventure. This is about empowering yourself with knowledge, turning that spark of wonder into a sustained flame that will keep you connected to the greatest story ever told. The story of our universe and our place within its invisible architecture. And so, as this journey draws to a close, it's worth pausing to truly appreciate the magnitude of the adventure we've just shared. We set out to map the invisible, to trace the hidden skeleton of the cosmos, and in doing so, we've connected dots across billions of years of cosmic history. This isn't just an academic exercise, it's a fundamental reshaping of how we see our place in the universe. Every time we look up at the night sky, we're no longer just seeing stars, we're seeing the glittering tracer lights of a vast, dark matter framework, a cosmic web that connects every galaxy, every star, and by extension, every one of us to the very fabric of reality itself. This hidden architecture is the greatest story ever told, a narrative written in gravity and dark matter, and we are now among the first generations to be able to read it. The real magic lies in realizing that this story is still being written. Our understanding of the cosmic web isn't a finished book sitting on a shelf. It's a living, breathing field of discovery where new chapters are being added with every new telescope launch and every new supercomputer simulation. The mysteries of dark matter and dark energy are not dead ends. They are the next frontiers, the exciting questions that will drive science forward for decades to come. This ongoing quest is a testament to human curiosity and our relentless drive to understand the universe we call home. It's a shared human endeavor that transcends borders and backgrounds, uniting us all in awe of the cosmic spectacle. I'd love to hear which part of this cosmic map resonated most with you. Was it the mysterious pull of dark matter, the ancient light of the cosmic microwave background, or the mind-bending future of the universe stretching into darkness? Share your thoughts in the comments below. Let's keep this conversation going. If you enjoyed this deep dive into the architecture of space, make sure to subscribe and hit that notification bell so you can join us for the next adventure into the unknown. Thank you for your time, your curiosity, and for sharing in the wonder. Together, we're peeling back the layers of the cosmos, one revelation at a time.